thank the organizers for inviting me and allow me to try to convince you that car molecules deserve to belong to this exclusive family of topological materials. And then I think in the talk that follows, or then Milo would show you that they are relevant also to superconductivity. So together we cover the subject of this meeting. So car molecules, I hope it will work. So here we are. So we are speaking about an effect that we call the car-induced spin selectivity effect, in short SPICE. And as I will discuss, we have two players in the game, car molecules and spins. So I'm not going to tell you much about spins, but I want to mention something about car molecules. Chirality in molecules means simply the structure of the molecule, of the equilibrium structure of the molecules, and it can be right or left-handed. And car molecules are really important because they play a major role in nature. Amino acids, sugars, DNA, all are chiral. And interesting question is why chirality is preserved so persistently through evolution. Also, the evolution, chirality maintained with no mutation. And the question why it was important for nature to preserve chirality, I will try to answer part of this question. And the second issue is that usually in chemistry, when we have closed shell systems, namely all electrons are paired, people think that the spin doesn't play a major role in defining the reactivity of the molecules and the interaction between molecules. What I will show you here, that this is not true when we speak about car molecules. How it started, how did we discover the effect? About 30 years ago, people started to study the interaction of spin polarized electrons with chiral molecules in gas phase. That was sort of a continuation of the work done with energy physics and nuclear physics. And they found that the effect, the spin on the scattering from chiral molecule is really very small. The cross-section is a 1/1,000,000th of a percent or so. It's very, very small. And when we saw it, we thought perhaps when we put the molecules on a surface, then the effect will be larger. So the experiment we constructed is based on having gold substrate on which we absorb self-assembled monolayer of chiral molecules, namely the molecules are well organized on the surface. And now we come with circular polarized light, typically with energy of between 3 and 4 electron volt. And the idea is to try to eject spin polarized electron. It's known that when you eject photoelectrons from gold, one can get a spin polarized electron if we use circular polarized light. So the spin polarization of the photoelectron ejected from gold is about 15 to 20%. So the idea was very simple. We flip the polarization of the light, and we look for the transmission of the electrons through the self-assembled monolayer into the vacuum, where we are able to measure their energy. And here are the first results that we obtained. Here, chiral molecules. This is a case of one-handedness. Here it's the other handedness, and here achiral molecules. So you see clearly that there is a big difference in the transmission. The difference is about 10%. So it's 10%. Remember that the spin polarized electrons are only 15 or to 20%. So it means that we have an effect here of about 70%. That means a huge effect of the spin. And we kept working on this, not actually appreciating the effect, till we collaborated with a group in Münster of Helmut Zacharias. And in Münster, they have a system that allows not only to detect the photoelectrons, but actually to spin analyze the photoelectrons that were transmitted through the monolayer. So basically, it's the same experiment, but then the electrons that are photo ejected through the monolayers are analyzed by mode detector, and this gives us the spin polarization. And in this experiment, what we found that there is very high spin polarization, and the spin polarization, in this case, the molecules are DNA molecules, it's helical molecules, and we get spin polarization that's going up to 60% polarization, namely a ratio of 1 to 4 between the two spins. And you realize that the spin polarization increases with the length of the molecule. This is the number of units in the DNA, between 40 to 72 units, and you see that the spin polarization is increasing from 40% up to 60%. And that's what you see here are the reference that we do all the time to be sure that the detector is working properly. So that was a really clear, direct evidence that there is a spin polarization of electrons passing through chiral molecules. Now, you should appreciate the fact that despite that the molecules here were adsorbed on gold, actually, even if we ejected photoelectrons with linear polarized light, namely there is no spin polarization, spin polarized electrons ejected from the gold itself, only by passing through the monolayer, we got this high spin polarization. And the first attempt to explain the effect was done immediately after we published our paper. And why there is a need to explain it. The reason is that the spin-orbit coupling in hydrocarbons, in organic molecules, is very, very small. So by very small, I mean fraction of milli-electron volt. And it is surprised that with such a low spin-orbit coupling, one can get spin polarization. So in this work that was done by the group in Dresden, they used basically a one-dimensional model of an helix. And what they realized that because of the curvature of the potential, of course, in the rest frame of the electron, there is an effective magnetic field. And this effective magnetic field can create effective spin orbit coupling of about 3 to 6 milli-electron volt, almost reaching to the value of the spin orbit coupling in carbon, which is much larger than the typical spin orbit coupling in hydrocarbon molecules. And the effect was observed in this simulation, in these calculations, but the size of the polarization was very low. The polarization typically was a few percent, while, as you saw in the experiments, we saw polarization of 40 up to 70%. Then another theoretical work was done by Karen Michaeli from the Weizmann Institute, and she introduced two new parameters in this model. First of all, a model is not one-dimensional anymore. Here, she used a tube, and therefore there is another degree of freedom that perpendicular to the velocity of the electron. And apparently this degree of freedom is very important for the obtaining the spin polarization. The second thing she introduced barrier in the form of a dipole moment, but it can be any other barrier. And this barrier causes the enhancement of the spin polarization. So she was able to obtain spin polarization of up to tenths of a percent. And that was nice. But the question was, is this sufficient? In parallel, we did experiments, and now not photoemission experiments, but real conduction experiment. So we have a substrate with magnetized, either we can magnetize either up or down. We adsorb chiral molecules on this substrate, and we come with a conductive AFM tip, and we measure the current through the molecules when the substrate is magnetized in one direction or the opposite direction. And here are the results. You see the IV curves as we measure them. This is the log scale. And you realize, first of all, that we get spin polarization very similar to the spin polarization obtained in the case of the photoemission, which is quite surprising because here we are in the bound electron regime, not in the free electron regime. And the second thing is that clearly there is different threshold for conduction for the two spins, and the conduction, the IV curve is definitely not in linear, not in the linear regime. So we have a non-linear effect here. And then we did length dependence, and as observed in the photoemission, also here we observe about linear dependence on the length of the molecule. That's the double-strand DNA, and this is a case of oligopeptide. Oligopeptide, for the people that don't know what it is, it's basically amino acids that are chiral that are bound together to form a short polymer of about 28 units. And this polymer has a shape of a helix. So in both cases, we get nice spin polarization. And please realize that we are speaking here on the length of 3 nanometers. So 3 nanometers of molecules is enough to give us spin polarization of 45% at room temperature. That's quite impressive, and you will see things will become even more impressive. But another interesting thing is to check the length dependence for each spin. And you realize here that while one spin decays very fast, it's a log scale, the other spin decays very slowly as function of the length of the molecule. This should remind you that a typical topological case where the spin is protected by the linear momentum, and you realize here that for one spin is going farther away because backscattering is reduced due to this, if you like, here I allow to say through this topological effect. So the finding, if I would summarize so far, we see IV curves that are not linear. There is different threshold for each spin conduction. This, together with other work that was done by us and by others, indicates that there is no spin flipping inside the molecule. So it's a real filtering, but not spin flipping. The polarization is similar to that obtained with photoelectrons. Then we went forwards to try to understand better the source of this spin polarization. In other words, what molecular parameters affect the spin polarization. And here we joined forces with Bert Meyer from Eindhoven, and Bert is organic chemist, and he synthesized these molecules. And these molecules, as you see here, are not chiral, but on the side, he put chiral molecules. And then these molecules are assembled inside solution to make wires. And if the side groups here are chiral, they make chiral wires, as you see here. Now, what is the handedness is the wire depends on the handedness of the side groups in these molecules. So you can make these wires chiral, right-handed or left-handed, or you can make them basically not chiral if you have not chiral group here. So we took these molecules and we measured again with our AFM the conduction. But please realize that here the wires are lying on the surface. So they are quite long wires, micron long, but their thickness is varying between 15 to 20 nanometers. So we are measuring here the spin dependent conduction perpendicular to the axis of the wires along their diameter. And here are the results for different molecules. And what you see here are the IV curves, and here is the spin polarization as a function of the potential applied. And you realize here we get up to 90% spin polarization. Huge number. 90% spin polarization means ratio of 1 to 20 or so between the two spins. As you see, you can see it clearly here. We have a very good selectivity here. But what was really interesting is when we did what is called surgeon and soldier experiment. What it means, surgeon and soldier? That's a technique used by people making this supramolecular structure. What they found that if you take achiral molecules and you dope them with few chiral molecules, the chiral molecules are like surgeon. They enforce the soldiers, the achiral molecules, to assemble in a chiral shape. And you can measure it by use a CD spectrum, namely measuring the optical activity of the molecule. And here you see the measurement of optical activity when you change the fraction of chiral molecules within the achiral molecules. And you realize in the beginning, when you introduce more and more chiral molecules, things are linear, but then there is amplification, and the chirality is induced by the chiral molecules on the achiral one, and we get very high chirality, even though only 60% or so from the molecules are chiral. And then what we did, we took the same molecules here that were measured here, and we measured the spin polarization through them. And to our surprise, we found that the spin polarization really follows the optical activity of the molecule. That we had hints towards this effect before, but here it's a clear proof that the spin polarization, or the cis effect, if you wish, relate directly to the optical activity of the molecule. And that was something that was not predicted or expected according to the old models used before. So what we learned so far is that we can get very high spin polarization. The effect is proportional to the optical activity. Backscattering suppressed for the favored spin. So what is missing in most of the models that was presented before? First of all, they were not able to explain the really huge, up to 90% spin polarization that was observed in several experiments. it is important that spin-orbit coupling by itself cannot make it. They do not explain the relation to optical activity. Indication where the answer stay is in the work that was done by Jonas Franzson, in which he included in the model electron correlation, and then he obtained very large spin polarization. So before continuing, I want to explain to you, since most of you are physicists, not like me, I want to stress the difference between molecules and mesoscopic structure, which you are using very often. First of all, of course, is the size. In molecules, we are speaking about nanometers, while, as you know, in most of the mesoscopic device, we are speaking hundreds of nanometers, perhaps more. Secondly, the density of state in the molecule is very low. As a result, when a molecule is attached to anything, there is a redistribution of the electronic state in order to match the electrochemical potential of the substrate. That causes a big effect in the electronic structure of the molecule. In addition, issue is that what happens when we apply electric field. While in most mesoscopic devices, when you apply electric field, the field is screened quite immediately after the interface. In the case of molecules, because of their size and because of the low dielectric constant, typically their size is below the screening length. Namely, all the molecule feels the field, and that results in a stark shift of the electronic state. In addition, when the electron or hole are passing through the molecule, the simple fact that you have additional charge on the molecule also affects the electronic structure. Therefore, any model in which you calculate first the electronic structure and then you calculate conduction by Landau formula or other way, such model is in principle doesn't include all the story in this system. So we see from this that because the field itself changes the molecule, the conduction from molecules basically almost never will be linear. It will never be depend linearly on the voltage, and the electronic structure should be calculated with the extra charge, with the contact, and everything else to be included. So I'm not going to show you now a full theory. I want to give you a hint how the story looks as far as I understand it. So let's assume we have a molecule, chiral molecule, and the chiral molecule is between two electrodes, two leads. You should appreciate that even if you have a donor and acceptor groups and you photoexcite one side, that's behave exactly like two leads. So in that sense, there's no much difference. So what happens when we apply voltage? When we apply voltage, because of the field, we polarize the molecule. Now, what is typical for chiral molecules, the polarizability of chiral molecules is anisotropic. Namely, there is different polarizability for right moving current or left moving current. As a result, with a very little spin orbit coupling, we get different charge distribution. It's a transient, it's only transient effect. Different distribution for the two spins. So if we started with a closed shell system, now because we apply a field, we get a transient effect in which one spin moves faster than the other. And now when electron has to penetrate into the system, it faces a spin here. So there is a spin blockade. Now this spin blockade is very substantial in molecules because the exchange is very strong. So typically in molecules, the exchange interaction is on the order of 1 electron volt. So even if we have only 3% or of a spin polarization, it amounts to 30 milli-electron volt change in the threshold for injecting one spin over the other. So what we believe happens in this cis effect is a combination of a small spin orbit coupling, relatively small spin orbit coupling, that amount to very small spin polarization, but then it is enhanced by the spin blockade. So it provides us this model provides us the largest difference in barrier for injection of the two spins, as we observe. So basically, exchange interaction plays here an important role. The spin polarization depends on the anisotropic polarizability of the molecule, and this is exactly proportional to the optical activity of the molecule. So we related now the cis to the optical activity. You should realize no coherency is required. The conduction can be non-coherent and it will not affect the results. Now I'll switch to some applications. So the first example is a work that I did together with our chairman, with Yossi Paltiel, and here what we did, we adsorbed Chiral molecules on a surface. And I want to call your attention to the following model. What happened when Chiral molecules is approaching the surface? Because of the different electrochemical potential, there is a charge redistribution in the molecule. Also because of the induced dipole effect. As a result, we get a transient spin polarization, as I mentioned before. This transient spin polarization means that at each electric pole, for a very short time, there is spin polarization, and which spin is related to which pole depends on the handedness of the molecule. So for one enantiomer, we have, let's say, spin pointing this direction. For the opposite enantiomer, it will be the other direction. Now, if we have a ferromagnetic substrate, clearly the interaction here will be different than interaction here. If you like, we have a low spin case here and high spin case here, and the energy difference between them is very significant. Actually, Yossi's group measured it, and we are speaking about more than 100 milli-electron volt. Again, you should appreciate this effect is a spin exchange interaction, and that's why the values of the interaction is very high relative to room temperature. So, what is observed? There is a ferromagnetic substrate, not magnetized. On a patterned surface, Chiral molecules are adsorbed. These molecules have one enantiomer, and here you see the opposite enantiomer. And what you see here is the topography as measured with AFM. Now, one can come with magnetic AFM and measure the magnetic field associated now with the ferromagnet. And it's a real surprise. One sees here that for one handedness, the field is pointing up, for the other, it's pointing down. And the reason is, if we go back for a second for here, The reason for this is that in order to bind these molecules, the free energy is minimized if the spins are pointing this direction. So the system wants to minimize the free energy by flipping the spin in the ferromagnet into this direction to have the strongest binding energy. Here, it would be the opposite. So in the case of the other enantiomer, the spin has to point down in order to minimize the energy, and therefore the direction of magnetization is changing. Related experiment is an experiment done together again with Yossi and Dave Waldeck from Pittsburgh. And what we did here, we absorbed on a ferromagnet Chiral molecules, and we use Kelvin probe to measure the contact potential difference as a result of this adsorption. So what we do here, we have a surface that vibrate relative to the substrate, and as a result, we create here a field. As a result of this field, charge is moving into the molecule or out of the molecule, and we compensate it with a voltage here. So we measure the effect of the adsorbed molecules on the work function. So here are the results. You realize that if we have a right-handed molecules, we get the south pole, the magnet pointing so the south pole is up, we get lower potential than for the north pole. For the other enantiomer, it's the opposite. If we have achiral molecules, we get no difference, of course. This means that depending on the enantiomer, it's easier to inject charge to one enantiomer than to the other. Everything depends on the spin that we align. Now we go to another application where we try to make magnet without ferromagnet. And the idea is the following. We took aluminum gallium nitride to the structure here, we have to the electron gas. We pattern on it whole device. But now, instead of applying magnetic field, as typically done with whole device, we adsorb on the surface Chiral molecules, and on top of them, we attach cadmium selenide nanoparticles. Now we shine light on this nanoparticle, and when we shine light, charge is transferred from the nanoparticle into the substrate. If the charge transfer is spin dependent, we expect to be able to measure Hall potential. And sure enough, we turn on the light, and the light is it's circular polarized, either right or left, and you see that we get Hall potential, which depends on the circular polarization of the light. And if we compare it to magnetic field, it amounts to about 100 Gauss magnetic field. So it's at room temperature, we get here effective magnetic field only by injecting spin from Chiral molecules into the gallium nitride nanoparticle. We continued and we did an additional experiment, and this time we made basically the same device, no nanoparticles. Instead of nanoparticles, we put an insulating layer on top of which we put a gate. And now we applied voltage between the gate and the 2D electron gas layer, and we measured again the Hall potential. What we observed was very surprising. We turned on the voltage, and as long as the voltage was on, we measured Hall potential. When we turned off the voltage, it turned off. If we used chiral molecules, there is no effect. Here you see the same effect when we change the gate, either up and down. Again, you see the same thing. What is surprising here, that it's clear that when we inject spins, we expect to see Hall signal. But how we keep the spins so long all through the time that we apply the voltage? What keeps the spins there? Now, to be sure that there are really electrons there, we use microwave absorption, and clearly in the microwave signal, we see the electrons, the unpaired electrons that we injected due to the voltage. So somehow, using the voltage, we inject electrons with spins, and these electrons with spins stay with their spin as long as we apply the voltage. So what's going on here? Here again, we were lucky to have Karen Michaeli with us that explained to us the effect. So in principle, what we think happening here is that when we apply voltage, we inject part of the wave function from the chiral molecule into the substrate. It is spin polarized. And now, due to indirect exchange, we keep the magnetic phase as long as this charge is injected. The proof for this magnetic phase is actually comes from the fact that we detected the Hall effect that we see is anomalous Hall effect, which is consistent with this picture. But still, the question is, how can it be that we inject spin so long? And here, there is a model done by Jonas Fransson from Stockholm. And what he did, he showed that if you apply voltage on the molecules on top of a semiconductor that has impurity states here, and 2D electron gas back, due to chiral phonons, you can align the spins with impurities. And this is very long distance effect, can easily go tens of nanometers. That's consistent with other work that was done that show that indeed you can, if you like, lengthen the extent of the exchange interaction by chiral phonons. I'm not going with all the explanation now, but it's a very interesting feature of chiral molecules. Finally, I want to tell you about new results just now in press, and it's now we are not speaking about single molecule, but crystals of phenylalanine. These are again chiral amino acid, which binds copper ions. And this work, the material was synthesized by Ehud Gazit from Tel Aviv University, and the calculation were done with Oded Od and Leo Krennick, and some modeling of Jonas Fransson. So these are the crystals. We get crystals that are about 300 nanometer thick, about micron long. And what is interesting in these crystals, that the copper ions are arranged in 2D layers, separated by about 3.7 angstrom. And they show they are chiral, the crystals are chiral, the molecules are chiral, the crystals are chiral. And we measured first the conduction through these crystals using our regular setup of magnetic substrate and conducting AFM. And this, let's concentrate on this molecule here. It's regular phenylalanine. And what we see here, that this is for L. For L, we see indeed that this current for magnet up is larger than when the magnet is down. And for the D, we see the opposite. But interestingly, we would expect this to be simply the opposite of this one. And here we see that the D is suppressed. We took other molecules in which we replaced the hydrogen with fluorine. Then the chirality flips. And indeed, we see the opposite here. Here we see that the L here is again, sorry, the D here is strong, and while the L is weak. So the question, what causes this asymmetry? Why L and D are not really showing the mirror image picture as we expect? The only way to explain it is if the system is magnetic. So we went and we measured the magnetic properties of the system. And sure enough, what you see here is the magnetism for when we have a parallel or perpendicular pointing magnet. And this was measured with a squid. And to our surprise, we found that while in room temperature, we have really nice hysteresis here, and the coercive field is quite large, when we cool down, it disappears. And there is a very large anisotropy here. For the parallel, we see larger coercive field, and you realize it really saturates very quickly. Parallel means the layers, the 2D layers, the perpendicular layers behave the perpendicular magnetization behaves differently, but in principle we see the same properties. So the question is, how can it be that we get ferromagnetism that is activated by temperature? And here is EPR study, electron paramagnetic resonance studies, and without going into the details, what it shows us that somehow the exchange interaction get more delocalized when the temperature is going up. And to add to this story, we conducted measurements as function of temperature, of course, conduction measurement is function of temperature, and you realize something really interesting. As long as the system is ferromagnetic, we get very low resistance. Once it becomes antiferromagnetic at low temperature, we get really high resistance. And at room temperature, we get this hysteresis. Here, this interesting loop, which it's like myristor, but only to hint, it's not like the oxide myristors, it's the opposite. Here, actually, the conduction is improving when we have current going in this direction, while typically in regular myristor, the current is reduced when we go in this direction. So how we explain it? So first of all, from the calculation, we see clearly that there is a ferromagnetic state and antiferromagnetic state that are about to degenerate. And you realize that these states are there because there is a strong exchange interaction between the copper ion and the lattice. And this exchange can cause the system to be either ferromagnetic or antiferromagnetic. But the interesting question is, okay, we can along the layer, but what correlates the spin in two different layers? That cannot be explained by indirect exchange. So here we propose the following model. Basically, we think that at low temperature, we have some exchange interaction that make the system either ferromagnetic or antiferromagnetic. The temperature slightly increases, then we get into a paramagnetic state. But then when temperature is going even farther up, the atoms are moving in the cavity, the copper ions are moving towards the lattice. And when they are moving towards the lattice, what happened now, they are spin polarized the lattice, because the charge on the cation attract charge in the lattice. This charge that moves through the chiral lattice is now spin polarized. And as a result, there is an exchange interaction between the ion and the lattice that becomes stronger. That's consistent with the EPR results. And each layer does it independently, but because the chirality is the same, they are all arranged in the same polarization. And so it's interesting that here the lattice mediates the spin polarization, but not by interaction through the lattice, but just having the right symmetry. And here is the model calculation. So you realize that that's the antiferromagnetic state, that's the ferromagnetic state. When the ions are moving towards the lattice, there's a splitting in the ferromagnetic state that brings it below the energy of the antiferromagnetic state. And that's create what we observe here. So we think that we have a very special case that because of the chirality of the lattice, together with the large motion of the ions as function of temperature, we create, if you like, a temperature activated ferromagnetism. So to summarize this effect, I believe that chiral molecules, because of their topological properties, are very efficient spin filters and allow also for long range electron transfer. That's why they may be important in biology. The spin-related interaction enhances the non-selectivity in nature. The effects result from many electron interactions. It's not a single electron picture. And important conclusion is the spin exchange plays a very important role. It's not the spin-orbit coupling alone that can make this effect to happen. Here are the people in my group that were involved in this group, in this work, and specifically I want to mention Francesco Tassinari, who actually helped me in all the operation. And here are many fantastic collaborators. I like to mention specifically Karen Michaeli from the Weizmann, Yossi Paltiel, who you meet now, David Waldbeck from Pittsburgh, and Claudio Fontanesi from Modena. And thank you very much.